All right, how's it going, everyone? We're back. We're going to be looking at conditionals again today, but now we're going to put a little spin on them and talk about independence again from last chapter. So just a little review. Remember that if two events are independent, the probability of A and B is equal to the probability of A times the probability of B. And we established last lecture, P of B given A is P of A and B over P of A. I know that I'm going back and forth with A and B, A intersect B. They're both the same thing. They can be written the same way. But it's important here that if we consider A and B as our numerator, and we have this rule from before, under independence, we would be able to rewrite this probability statement. So I'm going to take this and say that if A and B are independent events, P of B given A is still P of A and B, but in reality, we could rewrite that numerator as P of A times P of B, and then keep the denominator of P of A. Right? So again, this is if they are independent events. That's a very specific statement that I'm making. Now, as you look at this fraction on the right-hand side, you may notice I have two things, one that appears in the numerator, one that appears in the denominator, that actually cancel. These P of A's would cancel under the independence rule, and I would be left with P of B given A equaling just P of B. So if A and B are independent events, P of B given A is equal to P of B. And we kind of use this as we'll call it a test, but it's not really a test. It's just a check to see whether or not events A and B are independent. So one way we can check and see if they're independent is to see if P of A and B is equal to P of A times P of B. The other thing that we can do is, when given information about a conditional probability, to see whether or not it just equals P of B, that event that is occurring after A has already occurred. So that's what we're going to be looking at in this set of videos. So as a little refresher, here's our girls and boys that like to play sports and be popular and get good grades. And the question that we're trying to answer in this one is wanting to excel at sports independent of sex? In other words, do girls and boys, does it matter what your gender is, or I'm sorry, does it matter what your sex is? Will they choose sports as something they want to excel at equally, regardless of their sex? And that's what we want to answer. To do that, let's start off by first having you calculate two probabilities. Can you calculate the probability of choosing sports and the probability of choosing sports given you're a girl? So please calculate those two probabilities, and then come back and we'll move through the rest of it together. So how'd you do? Did you get 0.188 and 0.120 as your two? Hopefully you did. If you didn't, let's just recap real quick. The probability that you choose sports, there's 90 people who chose sports out of the 478, versus sports given you're a girl, so restricting the denominator to 251, and then being a girl who chose sports, there were 30 of them, gives you the 0.120. So if I consider this, P of B, and I consider this P of B given A, if I want to see whether or not sports and sex are independent of each other, I should be able to say that P of B given A is equal to P of B. Well, they're not. 0.188 is definitely not equal to 0.120. So what this shows is that if you are choosing success in sports as a goal, it is not independent of sex. So sex and success in sports are not independent. There's something about being a girl, in this case, that is making it different than being a boy. I don't know if the girls are at a higher rate or a lower rate at this point. I just know that it is dependent on your sex, because these two values are not similar enough. All right, so that's how we're going to use this little rule moving forward. So on to the next page. If you look at this problem, what about grades and sex? Are they independent? Would you say that picking grades as a goal is dependent or not dependent on sex? So if we compare P of grades to P of grades given girl, or we could have done it for grades given guys if we wanted to, but we're sticking with the girls here. Calculate the probability that you chose grades as your goal versus the probability of grades being chosen given you were a girl, and let's see how close these probabilities are to each other. So go ahead and do that. Okay, and here's what I get. I get the probability of grades is 130 over 251, or 0.518. And I get the probability of grades given girl as 247 over 478, which is 0.517. And lo and behold, guys, 0.518 and 0.517 are darn near identical numbers. I mean, to the nearest 10,000, to the nearest thousandth, they're almost the exact same probability. So we have some independence here with grades and sex. Oh, what's that? Oh, do I have those reversed? Did you just write them down in your notes like that because you didn't try them on your own? Oh, you guys are right. I actually have those reversed. That these fractions should be on the opposite side. Clearly, the restriction of girls is the 251, and the total number of people was 478. So go ahead and change those. I'm sorry if you have to erase that, but maybe that'll teach you that you should be writing some stuff down on your own. And maybe you caught it and you were getting all batty and you thought you were going to be able to write me some nasty email, but the trick's on you. Either way, though, these are independent events because those values are really, really close to each other. Someday we'll have a talk about how close they need to be, but it's really getting back to that, I think it was like chapter 3 where we did the two-way tables, or maybe it was chapter 4, where we said it's more your argument. If you believe that these values are close enough to say that they're independent, then yes, we'll say they're independent. But if you believe that they're too far, you could have an argument. They're not perfectly independent. 1817, they're not the exact same number, but I think we would all agree that they're really, really close. So that's about as close as we're going to see in the real world to independence. So why don't you guys go on to example number 6, are living on campus and having a meal plan independent? And then there's a second question there, are they disjoint? So I just felt like throwing that one in there. So go ahead and do example number 7, and then we'll talk about it. I hope that when you guys go off to college, the first time you go to eat at your dining hall and you're having the meal plan, I hope you think about this problem that we have now beat to death by going over it like 4 different times, this living on campus and eating on campus. You'll just remember stats class. So I'll give you a big wink from the sky when that happens. So here are the probabilities again. First question, why don't we answer the first question, are they disjoint? And right off the bat, hopefully you're like, heck no, they can't be disjoint because they have an intersection. The intersection of L and M is 0.42, so there's no way that they're disjoint. And that's good because this would be a really easy question to answer if they were disjoint, because we know that if 2 sets are disjoint, there is no way that they're independent. Independence is out the window for disjoint sets. So we need to do a check here. We can't just automatically say that they're not independent now. Now we actually have to check and see if they're independent. So I don't know what you were thinking, but I think I'm going to go here. I'm going to check is the probability of living on campus given the meal plan equal to the probability of living on campus. That's how I'm going to go about checking it. You could check meal plan given living on campus equaling the probability of meal plan if you want to. Either way, they should show the same thing. So this should be the probability of L intersect M all over the probability of M, which L intersect M is 0.42. Probability of M is 0.62. And on the other side, is that equal to P of L, which is 0.56? And just to keep the equation, 0.56. So what's 0.42 divided by 0.62? All right, I get 0.677 for the left-hand side. So 0.677, and that's not equal to 0.56. Nope. So it does not look like these are independent. And if you look back way at the beginning of our notes, that was what we had hypothesized, and we had actually shown using P of L times P of M to see if it equaled P of L intersect M. It didn't work there. Here's just another verification that, in fact, meal plan and living on campus, not independent of each other. You're just more likely to have the meal plan if you live on campus. It only makes sense. All right, on to the caution page. This whole idea of independent and disjointness, from what I heard from you guys in class the other day, still seems to throw some people off. So we're going to make a few statements about disjointness, independence, and see if we can't clear this up one last time. So consider two disjoint events. I've given this example before. You get an, oh, excuse me, oh, that was dinner. You get an A in this class, you get a B in this course. I don't know why I use course and class. They're the same thing. They are disjoint because they have no outcomes in common. You can't have an A and get a B. You can't have a B and get an A. So suppose that you check our online grading system. It used to be this thing called iPass. You guys remember that? And you find that you did get an A in the class. Now, what's the probability that you got a B? Well, the probability you got a B just automatically changed because of your knowledge of getting an A. That means that those two events cannot be independent. So knowing the first event, getting an A, changed the probability for the second event, so they're not independent. So I have a few things that I want to write down here. I'm going to write them down and then come back and talk about them. So give me a second. I'm going to write them down. Then you can write them down. Pause it while you're writing, and then I'll talk. Oh, look who just got all fancy and went typing on you instead of writing. So here are the three things, and these are from your book. The first two I really agree with. The third one I'm going to put on there because you may run across it, but the wording of it's not my cup of joe. So the first one, disjoint events can't be independent, exclamation point. If I could capitalize it, I would. I don't know how to do that, though. You can't have disjoint events being independent of each other. If they have no common outcomes, if one occurs then the other can't, you're not independent. So clear as day, that one. Second one, two events can be either independent or disjoint, but not both. So you can't be both. There's no occasion ever where I can think of you having independence while being disjoint. You can be disjoint, not independent. You can be independent and not disjoint. You just can't be them both. The third one, two events can be neither disjoint nor independent. Don't really love this because, again, the neither nors, I know, throw people off. But this is really the last example that we talked about. Living on campus in the meal plan, they're not disjoint and they're not independent. So that's a case where they're both of them. They're not this one, nor are they the other one. So that's what we're talking about. All right, so just kind of keep these things. I know that you can probably visualize these appearing on some assessment sometime down the line. So make note of this page of your notes. And as a kind of summative look at conditional distributions here, can you take a look at example number 7 and see if you can answer questions A and B? Given the information in the table, are being male and having a supervisor job disjoint events? Is having a supervisor job independent of the sex of the employee? So take a little time to answer those two, and that will be it for this video. All right, so here are the two answers. For part A, I think it's easy enough to see that there are 8 male supervisors, so no, they can't be disjoint events because there are employees that are male and are supervisors. In part B, I chose to go with males again because we had just talked about males, but you could have done this with females. And lo and behold, there's no sexism here at this particular company because the probability of being a supervisor is not different regardless of being a male or a female. So if you look at probability of male, there's 40%. Probability of male being supervisor, 0.40, perfectly equal to each other. They are independent. If you did it with females, you get the other 60%. You'll find the probability of females is 60%, and the probability of being a female given being a supervisor is 60%. So again, independence would be shown. It wouldn't matter how you did it. All right, I have no idea what day it is that you guys are watching this video. I don't know if it's snowed out. I don't know what's going on. So I hope all is well. I hope you're getting excited about vacation, but you're not actually checked out yet. I will see you guys virtually at some point and in person at another. Take it easy.